So in chapter 12, what we're working on is trying to solve systems of equations. That means you have several equations that you're trying to solve simultaneously. You're trying to find some values of x and y, or in our current case, x, y, and z, that satisfy each equation in a little system. Now in the first section, section 12.1, we were concerned with 2 by 2 systems of equations. And basically that was asking us to find where two lines intersect each other. So that point of intersection was your solution. Now there was more than just that could happen. I mean, this is ideally what you'd like to see happen when you're trying to solve a system of equations, is you get one solution. But other things can happen in the 2 by 2 case. What are some of the other things that can happen? Good, you can get two parallel lines that never intersect. So if that happened, then there'd be no solution. So if you had something like that, and then another one, say like this, there's no solution. By the way, do you remember the vocabulary for that? That would be independent and inconsistent. Those terms are going to carry over to the 3 by 3 case. There was actually one last case that we could deal with. Very good. Dependent and consistent. So what's happening there is you have two equations that really represent the same line. So say the first line and the second line. One right on top of the other. So there's an infinite number of solutions. That's the dependent and consistent case. The geometry for a 3 by 3 system equations gets a little bit deeper. So instead of dealing with a line in a plane, you're dealing with the entire plane. So this equation, for instance, represents a plane. So does this one. So does this one. And what you're interested in finding is where those three planes can intersect each other at one point. Now try and use your imagination, the walls, the floor, and the ceiling of this room, to figure out a way that three planes can meet at one point. Where would it be? Yeah, it'd be at one of the corners, right? So in the upper right corner of the room, you have three planes, the front wall, the right wall, and the ceiling, that meet at a corner. So that's how three planes can meet at one point. But, you know, the geometry gets a little bit crazier. You could have something like this, three planes all the same. You could have three planes meet along a line, in which case you have an infinite number of solutions. Two planes that are same, one that's parallel. Three planes that are parallel, two planes that are parallel, and one that goes through it. Now, by the way, how about this one down here? Three planes that are parallel, or two planes that are parallel, and one that goes through it. Is there a solution to that one? To part B here? Is there going to be a point that's on all three of those planes at the same time? No. So there'd be no solution here, no solution here, no solution, infinite number of solutions, and again an infinite number of solutions. What we want to see is one solution. So that would be the aforementioned corner point in a room. But there's a lot of things that can happen. It still boils down to the same three cases. The number of solutions you're going to get is 1, 0, or infinity. Which is kind of, you know, pretty wild, diverse set of choices. But let's pay lip service to one of the early problems and then kind of move on into how are we going to solve these kind of things. So problem number 12 and 13 give you a set of numbers and say, is this a solution to this system of equations? So how could you decide it? How could you decide whether or not -3, 2, and 1 is a solution to this set of equations? Good. Plug it into each of these equations. Now, something that I need to mention here, this is going to be x, y, and then z. So instead of ordered pairs, we now have ordered triples. There's a lot of different names that you can run into for this in different areas of mathematics. Another one that I like for that is a three-tuple, is what they're called sometimes. But call it what you like. These are always going to be in alphabetical order. A, B, and C, X, Y, and Z, R, S, and T. It just depends on the problem. But in order to see if this is a solution to all of these, you have to put it in one at a time and grind it out. And I think this one turns out to be yes. Or no, this one doesn't work here, but I think the second one does work. So if you want to check that at home later on, you can. Now, it would be an awful lot of work to try all the different combinations of integers that you could think of. That's not a good way to solve a system of equations. So what we need is something more methodical. So that's where the handout comes into play. Here's a system of 3x3, or 3x3 system of equations. So we have to somehow or another solve this. What I'm going to do is work you through the way I suggest you solve these things when you're solving them by hand. Later on in section 12.4, I'm going to teach you how to do this on your calculator, but I'm still going to ask that you do one of these by hand. So, how do we do this here? Well, my first goal in solving these things is to pick an equation. So, for convenience, pick something that has a variable that has a coefficient of 1 or negative 1. And here's what we're going to do. We're going to use this equation to eliminate one of the variables from the other two equations. Now, what do I mean by that? Well, since y here has a coefficient of 1, I'm going to use that to eliminate the y from this equation, and then again use it to eliminate the y from this equation. Let's see that. What would I have to multiply this equation by and then add here to get rid of the y term? Negative 2. All right, so negative 2 times row 1 added to row 2. This is going to be our new second row. So that's going to be negative 4x minus 2y minus 8z equals negative 24. And we're going to add that to x plus 2y plus 2z equals 9. So I get negative 3x, the y's cancel each other out, minus 6z equals negative 15. And just leave it there. Whatever comes out of this equation, just leave it. Because we've got to repeat this process for the third row. Are we okay with what we did here initially? We just got rid of the y from this row. Negative 2 times the first row. So negative 2 times 2 is negative 4. Negative 2 times 1. Row 1 plus row 2. Okay? Now, what do I need to do in a similar fashion to get rid of the negative 3y term here? Multiply row 1 by what? 3. So it's going to be 3 times row 1 added to row 3. 3 times row 1 is 6x plus 3y plus 12z equals 36. And I'm going to add that to 3x minus 3y minus 2z equals 1. So what equation pops out of that? Well, 9x plus 10z equals 37. So if you notice, I got that one and this one. So what I accomplished? What I accomplished was I got rid of the y's from two of these equations, right? Those two equations no longer contain a y. Now that's good news, because now you can look at those two equations and focus on those. So this is a 2 by 2 system of equations. How do you want to solve it? What are your choices in solving a 2 by 2 system of equations? You have three. Good. Good. Substitution, addition, and what's the last one? All right, graphing. All right, so substitution, addition, or graphing. Do we want to graph this to solve this? No. All right, me neither. So what else can we do? Well, let's do what they suggest here. Let's do the addition. If you multiply this by positive 3, that'll put a negative 9x here. What's the advantage of that? When you add it to the bottom equation, that cancels. I get negative 8z equals negative 8. So what does z equal? Z equals 1. Yay, z equals 1. Does that help me out at all? How does that help me? Colin? What can I do now? All right, we can solve for x. We know what z is, so let's plug that back in here and solve for x. Let's choose this equation just because, I don't know, just because all the things are positive here. So I get 9x plus 10z equals 37. 9x plus 10 times 1 equals 37. I'll subtract 30 from both sides. Or excuse me, subtract 10 from both sides. What does x equal? X equals 3. Let me pause for a second here. Can you see the advantage that we gained when we got rid of the y from those two equations? What did that allow us to do? How did that help us? Yeah. So by getting rid of the y from those two equations, we gave ourselves a little 2 by 2 system equations. You guys should be good at solving 2 by 2 system equations. We did it the other day. You did it in the previous class that you had before this one. So there's your 2 by 2. You can solve that any way you want. Graphing, substitution, addition, whatever you want. I'm not going to micromanage that. But now that I have x and z, what can I do now? Solve for y. So let's go back to, does it really matter what equation I choose here, you think? No, you can choose any equation you want. I chose the top one. So 2 times 3. And isn't this cool? This is for you guys who are not really morning people. This is the interactive handout. You get to actually do something. Plus 4 times 1. Keeps you alert. Ooh, let's answer it. Y plus 10 equals 12. So what does y equal? 2. So if you're doing this on WebAssign or looking up your answer in the back of the book, it'll be in this form. It'll be in X, Y, Z, that 3-tuple form. So 3, 2, and 1. That will be your answer. Isn't that special? Yeah. A church lady reference? No. No. One more time? Oh, yeah, yeah. Oh, yeah. Old Saturday Night Live skit. Yeah, that is kind of a reference that way. Yes. So the first step that we did was we multiplied this by -2 with the goal of getting rid of the y here. Okay, so we did that. added negative 2 times row 1 to row 2. Well, when you multiply this by negative 2 and add it here, it's going to cancel out the y's. So I got no y. So that became my new second equation right up here. I did the same thing here. I said, you know what? I got to get rid of the y from another equation. So I multiplied the top row by 3 this time and added it to the third row. And when I did that, I got this equation. So overall, I gave myself 2 new equivalent equations, neither of which had a y in it. And it's this 2 by 2 right here that I said, okay, this is special. I'm going to solve that. So I took it over here and said, all right, that's a 2 by 2 system equation. I can deal with this. Solve it by addition or substitution. We chose the addition method. Substitution wouldn't be that bad either. If you divided this by negative 3 everywhere, you could get an expression for x, easily solve. But I think your question was more up here. The nice thing that we did is we got rid of a variable from 2 of the equations. And once we whittled this down to a 2 by 2, we're able to solve it. So you're okay with that then? I could go back and redo this same system of equations. I could use this equation and get rid of the x's, and it would work out to the same solution. Yes, sir. You can do the 3 by 3 by an addition method. It would take a different skill set and some more practice and work. So I'm not going to teach it. That's close to something called Gauss-Jordan elimination with back substitution. It's not something I'm going to take the time to cover here. Question?
So for these, the 3 by 3, we have to use like elimination and get rid of one variable. We can't just like substitute.
Well, I'm not sure what you would substitute.
Because like in the first equation, like you can just subtract 2x and subtract 4z and then get y.
Oh, and then take that expression and plug it in here and say, okay, and then get x in terms. It'd be a lot of work. Yeah, it would take a lot of finesse and care to do it that way. Yes. It can be done. Yeah, but there's much more methodical ways. You're going to learn 2 more ways after this section. We're going to learn 2 more ways to solve a 3 by 3 system equations. So there's a lot of ways to do this. Yes.
Do you think that for these system equation problems, that the addition method is usually easier, or do you think it's better?
We're not going to do substitution for 3 by 3s. Just not. It becomes a real challenge. Okay. For the second part here, this part is totally up to you. Whatever's easiest. That's what I would encourage. Whatever's easiest. I mean, if you ended up with something, say like this, if you ended up with x plus 2y equals 7 and 2x plus 4y equals 14, you might be able to look at it and go, you know what? Those are really the same line. So I know I'm going to have problems. So you could stop. You can kind of figure out this by graphing, or you might be able to say, all right, well, I have, let's say, y equals 2x plus 5 and y equals 2x plus 7. Oh, gee, these are parallel lines. I know there's no solution. So that's really the only way that you can use graphing very easily. Other than that, I do substitution or addition. Yes, sir.
How do you know it's times that by 3?
Well, what would you add to negative 3 to make it 0? It would be positive 3. So since I have a 1y here, multiply 1 by 3, will give me 3. And that's what gave me the 3. So same thing here. If I wanted to get rid of the y here, I'd have to be adding the opposite. So negative 2. That's why I suggest you choose a variable that has a coefficient of 1 or negative 1 when you're doing this elimination, when you choose this equation. Notice that I chose this equation and I used it twice. I used the same equation twice. And I eliminated the same variable. I eliminated y from both of these. Let's do another one. I had some good questions. Let's do another. I can do the same one a different way if that would be helpful. No? Want to do something different? God, variety. All right. Let's try problem number 24. Five x plus 6y, or you know what? I'm going to rewrite problem 24. Problem 24, at least initially, starts out as a little bit of a mess. Yeah. Well, yeah, let me show you what the original problem 24 looks like. So, in problem 24, not everything is nice and neat on the left-hand side. So, what I'm going to do to start with is I'm just going to move these terms to the left-hand side. Now, when something switches sides, what else happens? Changes signs. So, yeah, you're just going to rewrite it. So 5x minus 4y. It should be minus. Minus 4y plus 6z equals 21. Is it negative 21? Oh, minus, yeah. Thank you. Equals negative 21. Then what else? Let's 9x plus 2y minus 3z equals negative 47. And last but not least, 3x plus y equals negative 19. Well, that's actually good news for us. Okay? Because what we need here is two equations that have just two unknowns. We've already kind of got one. This equation only depends on x and y, right? So if we could get another equation that just depends on x and y, we'd be in great shape. So, is there a way I can eliminate the z from one of these equations? What if I tried to use this row to eliminate the z from the first row? How would I do that? What do I multiply this by and add it here so that the z's cancel out? 2. So let's do that. Let me zoom out a little bit. So 2 times row 2 added to row 1. So 2 times row 2, let's start out with that. 18x plus 4y minus 6z equals negative 94. Added to 5x minus 4y plus 6z equals negative 21. And we get a bonus in this one, don't we? Does anyone see the bonus? I get 23x equals negative 115. Perfect. This is what I wanted. I wanted two equations that just had the same two unknowns. And that's these two. So 3x plus y equals negative 19. And 23x equals negative 115. But that's what I was looking for. I was looking to try and get two equations with the same two unknowns. Well, let's solve these. And you're free to solve these any way you want. In this case, I think I'd do substitution. Sort of. I'm not even sure if calling it substitution is the right word here, because we know what x is right here, right? You can solve for x. Might not be able to do it in your head, but what does x equal? -5. Just divide both sides by 23. Once I know that that's a -5, let's plug it into the top equation. So let's see. 3 times -5 plus y equals -19. So that's going to be the same as -15 plus y equals -19. Say again? Because I put in -5 for x. So 3 times -5. Last but not least, let's add 15 to both sides. And I get y equals -4. So 2 down and 1 to go. The two solutions I've got are x is -5 and y is -4. That's why I wanted a pair of equations that just depended on one variable. Okay, so I have x and y. I still need z. Dylan, what am I going to do to find z? Some help maybe? Yeah. Take x and y and substitute it in one of these first two equations. Why one of the first two, not the third one? Yeah, there's no z here. You wouldn't be able to solve for z if you plugged in because there's no z. So substitute in one of the first two. I'm just going to take the top one. 5 times -5 minus 4 times -4 plus 6z equals -21. So 25 plus 16 plus 6z equals -21. -25, thank you. So that's -5. As your -25 would be -9 plus 6z equals -21. Add 9 to both sides. 6z equals -12, so z equals -2. -5, -4, -2 is your solution on that one. At the end of this type of a problem, if you're looking at that going, you know, I'm not so sure about that one, what could you do to prove that you got it right? Plug it in the original. So if you take that, plug it in. What if it works in 2 of them but not the third? Yeah, then it's not a solution. Has to work in all 3 of them. Now, I don't see too many students taking the time to check it in all 3, but you can. You can know before you hand in your test whether you got that problem right or wrong.
So if they don't check in all 3, then you get something wrong. Is that what you're saying?
Exactly. It has to check in all 3 in order to work. All right, let's do another one that's a little bit more like our original one. And that would be problem number 18. (5x) plus 4y plus 2z equals -2. (3x) plus 4y minus 3z equals -27. And 2x minus 4z minus 7z equals negative 23. Excuse me, 2x minus 4y minus 7z equals negative 23. Now, unfortunately, this system of equations doesn't have something on the left-hand side that has a coefficient of 1 or negative 1. That's what I always look for first. But let's set that aside for a second. What we're interested in is trying to find a way to eliminate a variable from two of the equations. It doesn't matter which variable. Does there look like a variable that would be easy to eliminate from two of the equations? The y variable? Sure. Now you've got your choice. You've got three equations. They all have a 4 or negative 4 as a coefficient. Which one do you want to use to eliminate the y from the other two? Want to use bottom one? All right. So bottom was a good choice. I like that. Good job. So if I wanted to get rid of the y from the first equation, what would I do? Just add them, right? So I'm going to do row 3 added to row 1. Now you don't have to write this down, but if you do, if you keep yourself organized, it's easier for me to give you partial credit, and it's just a good way to keep organized. So we're adding row 3 to row 1. It's going to give us a new row 1. So 2x minus 4y minus 7z equals negative 23, added to 5x plus 4y plus 2z equals negative 2. So we do that, we get 7x minus 5z equals negative 25. And just leave it. Don't do anything with it right now. What are we going to do next? Anyone? Yeah. So we're going to add row 3 to row 2. So that would give me 2x minus 4y minus 7z equals negative 23. And I'm going to add that to 3x plus 4y minus 3z equals negative 27. Certainly a good half of the battle in this is just not making a typo. It's really easy to copy something wrong and screw things up. When we do that, we'll get 5x minus 10z equals negative 50. This is where I wanted to get to. I wanted two equations with the same two unknowns. So let's take these two equations. I've got 7x minus 5z equals negative 25, and 5x minus 10z equals negative 50. What would you do to solve these? Say again? Get rid of the z? Sure. How could I get rid of the z? Close. There you go. If you multiply the top equation by negative 2, you can get rid of the z here in the bottom equation. Another way that occurred to me that would work out pretty good, if you wanted to, if you took this equation and divided it through by 5, what would happen? What would I get if I divided that equation by 5? Minus 10. So if you divide out the 5, you get x minus 2z equals negative 10, or x equals 2z minus 10, like that. Now what could you do to finish solving? You substitute in the other equation and solve by substitution. So I'm just reminding you that there's more than one way to solve these systems of equations once you get down to the 2 by 2 part. which way do we want to finish up? Let's do one. Let's do this one by substitution, since I won't do substitution very often. Usually, I find it more convenient to use the addition method. That's what I typically do. But I want to remind you of this just for good measure. So it's going to be 7 times my expression for x minus 5z equals negative 25. So 2z minus 10. By substituting that there, I've got a linear equation that just depends on z. 14z minus 70 minus 5z equals negative 25. So 9z minus 70 equals negative 25. And then just solve. Add 70 to both sides, divide through by 9, and I get z equals 5. Yay. Yes.
You lost.
Okay.
After you did the 7x minus 5z to get like to cancel out the z, after you like multiply that top number by -2.
Oh, wait. I didn't multiply anything by negative 2. Oh, you mean? Yeah. No, you. All right. Sorry. All right. So I'll tell you what. For those of you, so we solve this by substitution here. And if you solve by substitution, then you can plug this back in here for x and get x equals 2 times 5 minus 10. 10 minus 10 is 0. So we get x equals 0. So that would be our two solutions. That's by substitution. Now, like I said, if you prefer, you can solve this one by the addition method. And that's probably what I would have done. If I was just working this on my own. You can multiply the top equation, 7x minus 5z equals negative 25. Multiply that top equation by negative 2 to get negative 14x plus 10z equals 50, added to 5x minus 10z equals negative 50. Negative 9x equals 0, x equals 0. Okay. Let's back up.
You wrote so fast that I got lost in all the numbers. I have no
Sure.
idea where.
All right.
I tried to write, but I got lost.
Let me summarize what I'm doing. Are you okay with how we got the 2 by 2 here?
Yeah, there I got it.
You have to solve this one way or another. What are your choices in solving this? Addition or substitution? So the first thing I did was I did it by substitution, which is all the work here. So I solved this by substitution, and I got 0 and 5. How did I solve by substitution? I took the second equation, and I divided everything by 5, which gave me a little bit friendlier equation, x minus 2z equals negative 10. And then I moved the 2z to the right-hand side so that I had an expression for x.
What did you divide by 5 though?
The second equation. Yeah, just to get a nicer equation. Because in the substitution method, you have to solve for either one of the variables, right? So I solve for x. Mindy? Hang with me.
Making notes. Sorry.
Okay. All right. No, I just didn't know if you're hanging your head in defeat or if you're okay.
My notes. So
Okay. Yes. Wait, here? Well, once we substituted, so let me finish solving it here. So we got this expression for x. substituted it into the first equation, and solve for z. And then we got down to here, z equals 5. I took that z equals 5 and I substituted it back into this equation. So this is solving by substitution right here. So it's taking this 2 by 2 and solving it by substitution. The other way to solve this system of equations is by the addition method. So the addition method is down here. Take and multiply the top equation by -2, and you get something like this. And if you add that to the bottom equation, you quickly get that x equals 0. If x equals 0, let's substitute that into one of the original equations. So one of the original equations was 7x minus 5z equals -25. 7 times 0 minus 5 times z equals -25. That cancels. -5z equals -25 means z equals 5. So one way or another, x, y, and z, we've got x is 0 and z is 5. We need to figure out what y is. To figure out what y is, you got to go back to one of the original equations and substitute. So to finish this one up, 2 times 0 minus 4 times y minus 7 times 5 equals -23. That comes from our last equation, substituting in what we know for x and z. So that's 0 minus 4y minus 35 equals -23. If I add 35 to both sides, I get -4y is positive 12. After which y is -3. Okay, let's take a break here, and we'll do some more when we come back.